Hello. In this section, I'm going to talk a little bit about implicit differentiation. Implicit differentiation deals with functions of which are not exactly explicit. Now, one way to kind of just understand what explicit means is that you essentially have your variable y is equal to some function of x, where that's pretty straightforward, that, you have a function with respect to x and then that you're just going to differentiate, and then you know that y prime is equal to f prime of x. There's no question about it. But whenever you have something like x times y equals to 1, or even like y squared equals to x, well, it's not really clear as to what is y. But notice that with x times y, I can rewrite it in such a way that y is equal to 1 over x, which means that y prime is equal to negative 1 over x squared. Well, that was easy. But notice that if we look at y squared equals to x, and then we figure out that basically we have two functions. We have y equals the square root of x, and we have y equals the negative square root of x. So it's not really clear as to what, you know, we're looking at, like whether it's when x or y is, I'm sorry, where y is positive or negative. So this would be 1 divided by 2 root x, and this would be negative 1 over 2 root x, and this would be prime, that would be prime. But if we just simply just took the derivative of each side respectively, essentially we're not going to get the exact same thing, but we would not need to account for is it going to be positive or negative and so on. So like for example, if I look at the derivative of y squared and I have the derivative of x, this is 2y times dy dx because of chain rule, and that equals to 1, which means that the implicit derivative is going to be 1 over 2y. Now notice that y was basically just the square root of x essentially, but here we don't really need to consider that because again it's not sure, or it's not clear as to is it the positive or the negative. And similarly, if we take the derivative on both sides with respect to x for x times y, you'll essentially sort of get the same exact thing. Um, but, in this sense, I didn't look for the explicit formula. I just stayed with y squared. So essentially all that you have to do is just take the derivative on both sides. So let's say that we want to look at finding dy dx for x squared plus y squared equals to 4. So if we go ahead and we do this one, then we can actually find the derivative of this by saying we have the derivative of x squared plus y squared equals to the derivative with respect to x of 4. Now this gives me 2x plus 2y times dy dx, but this equals to 0. Now if I solve this algebraically, I end up with that dy dx is equal to negative x over y. Now that's actually, pretty convenient because again, if I want to find the slope of the tangent that satisfies this equation, then in that case, it's always just gonna account for itself, if that makes sense. Once you have the ordered pair for this one. Now, note that if you wanted to find the second derivative or any other higher order derivatives, you would basically just use quotient rule. So I'm gonna say for this one that you do try. Okay, so go ahead and try to find the second derivative with respect to x. Okay, so you're going to find that that's going to be with quotient rule. Now, let me go ahead and show you that we can actually still use the tangent line. So let's say that we want to find the tangent line um, of x squared plus x times y plus y squared equals to 1 at, okay, so that's just going to be at the ordered pair 1 comma 0. Okay, so for this one we have to actually find the derivative on both sides. So we have 2x plus, okay, now we have to use product rule. So that's just going to be 1 times y plus x times dy dx, and then plus 2y times dy dx, and that equals to 0. Now notice that basically you can solve for dy dx just using some algebra. So you have that you would subtract that would be minus 2x minus y, all divided by just factor over here. So that's like x plus 2y. Now, if you go ahead and you find the slope of the tangent, you're basically going to find that the slope of the tangent is equal to negative 2. So you have that the slope of the tangent is equal to negative 2, but you have that when you use the formula, you have that that's going to be y minus 0 equals to negative 2 times x minus 1, which is y equals to negative 2x plus 2. So in this case, this is the formula for the equation of the tangent line. Now notice that you could have simply just plugged in 1 and 0. Why? Because at that point it's just algebra to figure out what dy dx is, because I didn't technically need it. So notice that if you would have plugged in 1, 0, 1, 0, you would have still ended up with negative 2. Okay, so implicit differentiation is not really that bad. It just requires that you use a little bit of algebra in this case. We can do one more example, such as like if I have, let's say that you want to find dy dx for x squared plus y squared is equal to, not, yeah, actually this is correct. Okay, so this will be x squared over 9 divided by 25, and this is equal to 1. So this is the equation of an ellipse. So basically, like if you were going to draw this in the x and y plane, you would basically find that, there's a minor axis of 3 and that there's a major axis of 5. So essentially you would have something like this. So in this case, like you could say like this is negative 3, this is 3, this is 5, negative 5, and that this is positive 5. So see like how over here that we can pick any point alongside this this curve and find the slope of the tangent. The only problem is that you might end up with some vertical tangents right here and right over here. But you have that there are some horizontal tangents right there and right there. Okay, so that's kind of interesting. Now, it would be more interesting, like for example, if we can actually find like higher order derivatives for this, because in that case, like the way that I kind of look at it is that this is an ellipse, of which, this is very relevant to planetary orbits, which means that if we can find, for example, like the first derivative, that's velocity. If we can find the second derivative, that's going to be acceleration. So that's actually a lot interesting. Anyways, so we go and we find dy dx. We take the derivative on both sides of x squared over 9 plus y squared over 25 equals to, okay, so this is going to be, let's see, okay, so that's going to be the derivative of 1. So this is going to be 2x divided by 9 plus 2y divided by 25 multiplied by dy dx, and this is equal to 0. Now, interestingly enough, when we go ahead and we divide everything, notice that you're going to get the following, that you're going to get that this is going to be 2y divided by 25 times dy dx is equal to negative 2x over 9. But when you multiply by the reciprocal, you're basically going to get that dy dx is equal to, so dy dx is equal to negative 25, negative 25x over, yeah, this will be over 9. Yeah, so this will be over 9y. So in this case, we have the implicit derivative of the ellipse with minor axis 3 units and major axis 5 units. So this is actually very accurate in this sense. But one thing that I want to leave you with is I want you to find the second derivative with respect to x for this ellipse. So try to find using quotient rule again, and you'll notice that the math it simplifies very nicely in this case. So yeah, try that out and see. But I'll give you a hint. Negative 25 over 9 is just a constant. Okay.